The first chapter in the bioengineering textbook this semester is an introductory chapter, and so today we're going to talk about some definitions and overview of biomedical signal processing. So basically, signals are simply variations of some form of energy, and these carry some information about what it is you're trying to observe. So the variable that carries this information depends on what kind of energy is involved. If the energy is electrical, then the variable is a voltage or a current, while if the energy is mechanical, the variable is a force or a velocity. So, for example, if you were trying to measure the gait of an individual or the step length, then that would be a mechanical measure, and you'd be measuring either the distance between steps or maybe the force of the step so that you could get some information about that individual's gait. The interaction or communication with a system or between systems is done through signals, and independent of the type of system or its scale or function, we have to have some way of interacting with some sort of signal of interest to us. So the photograph here shows a very old picture of a person with some what appear to be electrical currents transversing through the body, and then someone trying to make a measurement of that. So here's a table of some of the different kinds of energy forms and how those variables are associated with the body. So, for example, chemical energy. Some of the variables might be chemical activation or chemical concentration. And common measures here might be different ions in your blood, oxygen levels, CO2 levels, pH, hormone concentrations, and then any other measures that involve chemistry, chemicals, or chemical compounds. Mechanical energy variables might be position, force, torque, or pressure. Some of the common measurements here might include muscle movement, cardiovascular pressure, muscle contractibility, your heart valve, and other cardiac sounds. Electrical measures would be measures of voltage or current, and some of these kinds of measurements would be what I refer to as all the G's: electroencephalography or EEG, electrocardiography or ECG, electromyography, EMG. EOG is electrooculography. GSR is galvanic skin resistance. As a general rule, these are making an electrical measurement of something associated with the body through a sensor. Thermal measurements would be measuring a variable of temperature, and that might be body temperature or thermography. So signal processing basically involves the transformation of a signal to another representation. So why would you use signal processing? Well, there are four main reasons. One is to get more information from the signal. So as an example, back when people first started doing EEGs, the EEG technician or physician would observe the EEG signal as it came off on a strip chart, and if they saw anything that looked unusual in that time domain representation, it was a very qualitative, almost an art form. Now EEGs are digitized, and we do some calculations so that we have actually numerical features that we can look at that give us more information about what's present in that signal. A second reason would be to reduce noise or make the signal more reliable. A third reason would be to associate the signal with a disease. In other words, we're going to do some kind of classification. And a fourth would be to reduce signal bandwidth requirements. So here's a flowchart of a typical biosignal measurement system. And I want to point out that not all systems have this particular kind of a flowchart. Some systems have some components and don't have other components, but this is just one that tries to include as many things as you typically see. So you have your physiological or external energy system, and then we have some kind of transducer that's actually what makes the measurement and converts it from that energy to an electrical signal. There's then an amplifier detector, and this is usually um, a combined device that both detects the output of the transducer as well as does some amplification. And then usually there's an analog signal processing step before the signal is digitized. There's often some analog signal processing. And I should point out that sometimes all three of these, transducer, detector, and analog processor, can actually be combined into one single integrated transducer system. So the output from the analog signal processing step typically then goes to an analog to digital converter. There is some buffering or signal storage that takes place, and usually everything here is done within a computer. There's then some signal processing that takes place once the signal has been stored, and then it can then be sent to a classification system, or it can be sent directly to a display. This represents a system that is not necessarily real-time. So this would be a system, for example, where we're acquiring a signal and then we're going to do something to it later. There are also real-time signal processing, and sometimes those will have feedback loops that then control other things. So, for example, if you're measuring, real-time blood pressure or real-time heart rate, and then that's being used to maybe send out an alarm if that signal drops below or exceeds a certain preset threshold level. So sometimes signal processing can be used in real-time applications. Another example would be brain-computer interface systems, where the EEG signal from one or more specific locations is being used to control something. So the way this chapter is arranged is to go step by step through each element that's present in that block diagram that we looked at. And so we'll start with the transducer. A transducer is basically a device that converts energy from one form to another. And in measurement systems, all transducers are called input transducers. In other words, they convert non-electrical energy into an electronic signal. In signal processing applications, the purpose of energy conversion is to transfer information, not to transform energy or do work. So in electrical engineering in general, there are two different main branches of electrical engineering. One is the transfer of information. The other is the use of energy. So this particular category involves information transfer. So we have some energy variation that's occurring, chemical, mechanical, thermal, and we're using a biotransducer to measure that, and the output then is a varying voltage or current. So input transducers convert signals from other energy forms. And I should point out that sometimes these other energy forms even include other types of electrical energy. So the brainwave signal, for example, is an electrical signal. And so we're converting basically dipole oscillations within the brain, magnetic dipole and electric dipole oscillations within the brain, into voltages that come out of the sensor. So that would be the transducer phase. A lot of times the transducer itself, because of the way it's built, actually forms a little miniature electric circuit that has its own characteristics and can be modeled. So biotransducers, basically the energy that's converted to the by the input transducer, this can happen a couple of ways. First of all, it can be generated by the actual physiological process that's going on. So this would be your heartbeat, your brainwave, your muscle movement, your breath. Or it can be externally generated energy that then interacts with and is somehow modified by the body. And so this would include X-rays, CTs, MRIs, and ultrasound. So the transducer is often the most critical element in the measurement system, and it's often the limiting element in the measurement system. So a lot of times the technology is limited not by the signal processing or the computational ability. It's actually limited by the transducer and the transducer design. So that's a current, area of research that we see pretty often in electrical engineering. So this is primarily a repeat of the slide that we saw before, which gives energy forms and related measurements. The next step in the measurement system is the amplifier and detector. So the first stage and the design of this analog stage depends on the transducer operation. So if the transducer is based on a variation in an electrical property, then first you have to convert that variation into a voltage. Detector circuits can either be single-ended or differential, depending on the type of detector. The difference primarily is if you only have one sensing element in the transducer, then the transducer signal is single-ended. If you have multiple sensors, then you can generate a differential signal where two signals move in opposite directions. So I should point out that it is possible to have multiple sensors and they can all be acting as single-ended sensors. So we often, when we make frame measurements, we'll have multiple channels and we're not necessarily taking the difference between two channels. We do typically take the difference between a channel and a reference location. So sometimes you can have combinations of the two in an overall measurement system. But as a general rule, when you do the electrical processing, you're either treating that as a single-ended or a differential, depending on the type of detector you're using. And so that makes a difference in how the amplifier is designed. One example of a single-ended signal would be just a temperature measuring transducer that changes its measurement, changes its resistance with temperature. So you basically are using a constant current source, and as the resistance of this transducer changes, it's going to change the output voltage. So it varies in a very well-defined manner and can be very well calibrated. So this would be an example of a single-ended sensor. Another example of a single-ended sensor is the cardiac microphone. Basically, the cardiac microphone has a little piezoelectric element that produces a small voltage when it's deformed. So the amplitude of this voltage is increased by an amplifier, and that would just be a single input kind of amplifier. In this course, we will not get into amplifier design. In the biomedical instrumentation course, that's a big part of that course, is based on kind of the different kinds of sensors. How do you design the circuits that support that? So to close this part of the lecture, we'll talk about the filtering stage in analog signal processing. So once again, this is analog. This is the analog part of the signal processing. More and more, less analog signal processing is done. A lot of times when analog signal processing is done, it is because of the nature of the way the sensor is designed. So there may be some built-in capacitance to the sensor that you then have to work with because it's going to have some filtering effects just based on the fact that there's a capacitor in the sensor. So sometimes you're trying to either mitigate or take advantage of those situations when you do analog signal processing. So filter circuits are circuits that are specifically designed to alter the frequency characteristic of the signal in a very well-defined manner. The purpose is to produce an output signal that either has reduced or enhanced amplitudes within specific frequency ranges. So the way we define filters is by their basic type. Is it a low pass, high pass, band pass, or band stop? We define them by their bandwidth, which is the range of nominally unattenuated frequencies, and we define them by their attenuation slope. In other words, what filter order, how is filter order related to attenuation slope, and what is the initial sharpness of the attenuation slope. So I should point out that on bandwidth, bandwidth can refer either describe a filter or a signal. So we can talk about a filter bandwidth, or we can talk about a signal bandwidth. The definition is the same. A signal bandwidth would just be the frequencies contained within the signal. A filter bandwidth would be the frequencies that are contained the frequencies that are not attenuated by a filter. So a filter type can be illustrated by a plot of the filter spectrum. And so a spectrum plot shows how the amplitude of a signal changes as a function of frequency based on what the filter is going to do to it. So the filter gain is known as a transfer function, and it's basically the ratio of an output signal amplitude to an input signal amplitude, and that's a function of frequency. And so filter types then are defined in terms of the frequencies they do or do not attenuate. So in the next slide, we'll show the 4 basic filter types. So here, the vertical axis is filter gain. So a filter gain of 1 would mean that the output voltage of the filter is equal to the voltage that was input to the filter. So this frequency is just a relative scale. We won't even call it hertz or anything. We'll just say 1, 2, 3. So in this first example, you can see that for some lower frequencies, the output over input is equal to 1, and then something happens around 1.4, and suddenly the output begins to drop fairly significant as a function of the input. So we would call this a low-pass filter, because at the lower frequencies, output and input are equal. At the higher frequencies, output is equal to 0. The high-pass filter is just the opposite. At the lower frequencies, we have basically 0 output. At the higher frequencies, our output over input would be equal to 1. So we're passing higher frequencies, and we would say we are cutting off the lower frequencies. The band pass filter is a combination of those two. It has a range. So below that range, we are cut off, and above that range, we are cut off. And so what we're passing is in between. And then the final one is the band stop filter. The band stop filter basically passes all frequencies. In other words, your output over input is 1, except for some range where it's specifically designed to cut off. So with the exception of the band stop filter, filter types are named for the frequencies they pass and not frequencies they attenuate. Why would we want to use different kinds of filters? Turns out that a lot of times signal noise occurs either uniformly over all frequencies or will have more high frequency characteristics. So a low pass filter is often used to increase the signal to noise ratio and get rid of noise issues in the filter. Whereas the high pass filter, notice, will zero out DC or very slowly varying components. So the high pass filter is often used to eliminate DC or to eliminate drifts in the DC due to ground changes in your ground voltage that occur slowly. The band pass filter would combine the qualities of both of those. The band stop filter is often used if you know a particular range that's going to be troublesome. So for example, if you're in a typical signals lab, you're going to have noise at 60 hertz because of the power levels in the room. So 60 hertz noise, often you will see a band stop filter centered around 60 hertz. So that's a fairly common thing. So the next thing that defines a filter is its bandwidth. So bandwidth is defined in the frequency domain. The bandwidth of a signal is basically the range of frequencies found in the signal. So when we define this range, we have to figure out when it is or is not considered to be present. So basically, if the output over the input is greater than 0.707, then the frequency is considered to be within the bandwidth. If we take 0.707 and we convert that to dB, that ends up being 3 dB. So a frequency would be within the bandwidth as long as it is within 3 dB of the output over input being equal to having a gain of 1 or 0.707. So you convert ratios like 0.707 to dB by taking 20 times the log of the ratio of output over input. So 0.707 in output over input would be equivalent to 3 dB. A gain of 1 would be equivalent to a gain of 0 dB. So if you drop more than 3 dB, you're not considered to be in the bandwidth any longer. That 0.707 number, if you're measuring output voltage over input voltage, and you were to convert that to power, power is proportional to voltage squared. So 0.707 squared turns out to be 0.5. So basically the cutoff or the range of frequencies present within the bandwidth have to have greater than 50% power. So the concept of bandwidth extends to filters and other processes, including measurement devices. And it just means the frequencies that are included in the band of interest. So here are some examples of comparing gain and also looking at how the plots are done. So for example, plot A, this is a low pass filter. This is an ideal filter because you notice that it passes perfectly with an output over input equal to 1 until you get to 100 hertz. And then at 100 hertz, there's a vertical drop. So a more realistic kind of filter is not one that has this immediately square shape, but basically one that begins to transition at some level, at some frequency below that 100 hertz that you would define as your bandwidth, or as your, what we would call cutoff. In other words, meaning above that level, you don't consider the components to be present in the signal or the filter, and below that level you do. So when you have this kind of non-ideal shape, you take this 0.707 and project that out to where it intersects this attenuation slope, and that by definition is considered to be your bandwidth. So the passband then in this case would be to the 3 dB or 0.707 point, and the stop band would be above that. Here's another example where you have kind of a different shape in the attenuation curve, but notice the definition of where the 0.707 occurs is the same. Now, if you look at figure C and compare that with figure B, there's a little bit of an advantage to figure C, because let's suppose we're concerned with what are the frequency components present in a given band, say of your breathing rate. So if you have a system that looks like figure B, notice that some of your frequencies of interest will be attenuated or reduced a little bit by the physical filter itself. So it's going to distort your signal, because for this range where this knee of this curve begins to where our cutoff frequency is defined, you have a changing amplitude in the frequencies that are being passed. Also notice that you're going to pick up some frequencies in your signal that's being passed that are not frequencies necessarily that you would want, because you don't suddenly go, you don't have this perfect vertical slope. So different types of filters with different design impact this attenuation slope. And just depending on how stringent your requirements are, then that determines how you would design your passband and your attenuation slope of your filter. Figure D just extends this example to show you how this would work in a bandpass filter, where the passband basically goes from the 0.707 point on the left side to the 0.707 point on the right side, and so that would give you your lower and higher ends of the bandwidth. So the bandwidth of this filter, in the first three cases where you have the low pass filter, is basically going to be this 3 dB point. Obviously in this one, which is perfect, you don't have a 3 dB point, so that would basically occur on the vertical slope. In the band pass filter, your bandwidth would be the higher cutoff minus the lower cutoff. In this particular figure, notice that the horizontal axis is a logarithmic axis. That's done pretty commonly. If you don't do that, you get some really protracted slopes here, and you also don't get a good representation of a wide frequency range. So lots of times when we talk about frequency and cutoff and bandwidth and things, we're talking about orders of magnitude. So plotting on a log scale, on a semi-log scale, is fairly common. The gain axis, it's also fairly common to see that plotted in dB as opposed to gain. So this 3 dB down threshold, as we said before, it has an amplitude of 0.707 when it's not attenuated, and so that would be half of the power of the unattenuated power. So that's sometimes known as the half power point, cutoff frequency, 3 dB down point, etc. The signal can have either a sharp or a gradual attenuation of energy, but its bandwidth is still given by the 3 dB down point. And once again, when it rolls off at both low and high, then it has two cutoff frequencies, and the bandwidth is defined as the range between the two frequencies. So the filter order is a little bit more complicated. Basically, the slope of that attenuation curve is related to how complex the filter is. The more complex the filter, the steeper the slope you have. So if we talk about very simple analog filters, the complexity can be related to the term filter order. And it's basically equal to the number of independent energy storage elements that you have in the circuit. In a circuit, independent energy storage elements are capacitors or inductors. So if they're independent, in other words, if they can't be equivalently combined with another, then they're considered an independent energy storage element, and that determines the filter order. The higher the filter order, the steeper the slope in that attenuation region. Filter order can also be specified as the number of poles. So a second order system would be the same as a two-pole filter and would have two independent energy storage elements, usually two capacitors. So this is more just for your information if you ever hear this terminology, so you'll know what it means. So when a filter's frequency characteristics plotted in dB versus the log of frequency, then the slope of that attenuation is 20 dB per decade times the filter order. So a first order filter would give you a 20 dB per decade attenuation. That means if you design your cutoff frequency to be at 100 Hertz, that you will be 20 dB or one order of magnitude lower at 1000 Hertz. So a first order filter has a slope that approaches 20 dB per decade, and a second order would approach 40 dB per decade, and so on. So the higher order your filter, the more rapid your attenuation. And so that just means that you don't pick up extra components of a signal that you don't want. Why would you plot this on a log scale? So here's an example of the gain plotted just as a linear gain. So this would be output voltage over input voltage as a function of frequency in a linear plot. And you can see this crazy slope here of the curve. Comparing that with gain plotted in dB. So remember, the gain in dB is 20 times the log of whatever this number is. So 1 would correspond to 0 on the graph on the right. In this case, you can see that it's going to be fairly flat, and then you have this nice little knee, and then you approach a uniform slope of decreasing amplitude. That slope is 40 dB per decade. So we like this log plot because it allows us to see more clearly how the filter is performing over a wide range of frequencies, and also it allows you to clearly identify that this slope out here is 40 dB per decade, which would tell you immediately that this is a second order filter. So here's an example of a second order or two-pole filter compared with a 12-pole or 12th order filter. They have the same cutoff frequency. And so the you can see the 12th order has a much more rapid attenuation compared to the second order. So we would cut off these unwanted higher frequencies much more rapidly than if we just used the second order and we're picking up all this extra stuff out here. So higher order filters are better at high frequency noise reduction. So the initial sharpness, so let's go back here. Initial sharpness is referring to right at cutoff, what does the slope look like? If you increase your filter order, you increase the sharpness, and that also increases the complexity and thereby the cost of the filter, so that would be the disadvantage. So it is possible to increase that initial sharpness without increasing the filter order if you're willing to accept some trade-offs. And those trade-offs are you tend to get ripple or uneven behavior in the passband. So let's look at an example of that. This is a Butterworth filter, and you'll notice it has a fairly rounded initial sharpness. This is a Chebyshev filter, and notice right here at cutoff how sharp that cutoff is. But the trade-off is that whereas the Butterworth is fairly flat at 0 dB until you get near the cutoff, the Chebyshev has this ripple or oscillating effect that you see prior to cutoff. Sometimes you're willing to live with this in order not to pick up any of this stuff and to have this rapid decay. And remember, okay, it looks like this sort of gets bad out here, but remember that minus 20 dB is actually an order of magnitude cutoff. So if you were at 10 volts, then just in this little tiny space here, you've already reduced yourself to 10% of your original voltage. So as an example, if we have an electrocardiograph signal that has 1 volt peak to peak, and it has a bandwidth that ranges from 0.01 to 100 hertz, we would definitely want to reduce some of the noise in the signal at frequencies that are above 100 hertz. So this would be the example of the kind of specification that you would get to design a filter that would operate in this way. So if you want to reduce the noise in the signal by 80 dB for frequencies above 100 hertz, then that means from above 1,000 hertz, then that means from 100 hertz to 1,000 hertz, you would want to decrease by a factor of 80 dB. So since the signal bandwidth has to be 100 hertz, then you want the cutoff frequency to be right at 100 hertz, and you have exactly 1 decade or 1 order of magnitude to decrease that. So basically for an 80 dB reduction, you would take 80 dB and divide that by 20 dB per decade, and that would mean that you would need a 4th order filter in order to achieve that kind of reduction over that order of magnitude. Okay, in the next lecture we'll talk about analog to digital conversion, but we want to end this one at this point.